Let's take a look at this problem from your lab assignment, section 4.7. It says here that they want us to find the points on the ellipse 4x squared plus y squared is equal to 4. We want to find points on the ellipse that's farthest away from -1, 0. So there's a little graphic of that here. We have -1, 0, and we have a point on the ellipse, so we want to find this distance. In fact, I have a Desmos animation for it, where if I move this point, you can see that the distance is changing. So if I'm on the ellipse exactly at that point, then I have a distance of 0, and then I go further and further away. At some point this thing looks like it's stretched out, and then I can go all the way over here to 1, which is another point on the ellipse, and that has a distance of 2. So at some point over here it looks like it stretches the most before it comes back down. So the maximum distance would probably be somewhere over here, a little bit bigger than 0, less than 1, maybe even less than 1/2. And so that's what we want to find. So that's the graphics, the viewing, and drawing of the pictures, diagrams. And so what we want to do is we're actually trying to maximize the distance between the point, the -1, 0, and the ellipse. So the first thing that they ask for is a distance formula. So what's the distance formula? Well, our distance formula is this thing where you find the difference between the x's, you square it, you find the difference between the y's, and you square it. And you're kind of making a little Pythagorean theorem triangle here. And so that's what they're asking for. So we must maximize the distance between this point. And so if we let x be a point on the ellipse, xy be the point on the ellipse, then your x value that you're subtracting from is -1, and then your y value is this point 0. So that's what we're putting over here, except they put a plus sign here already, so we want to make sure we just put a positive one, because it's actually x minus -1, and then we have x minus 0. So we're trying to maximize this, and so what we would do normally is we would take the derivative of this thing, but this thing is a square root. It turns out that when we optimize a square root function, it's almost as good. It is as good as optimizing the square of it. So that would make things a little bit easier for us, and we're just going to optimize what's inside here. And so we're going to let s, according to them, we're going to let s equal to whatever's inside. This is just x plus 1 over here. So let's write what they have. X plus 1 squared, and then we have a y. So what is y? What we're going to do is we're going to use the ellipse as our constraint. So let's also make a note of that. Our constraint is equal to the ellipse, and if you look at this new function that we're trying to maximize, we have 2 variables, but we only want this as a function of only 1 variable, so we need to replace y. This, by the way, is just y squared, right? It's y minus 0. So when we replace y, we can just consider replacing y squared, because y squared is in the ellipse, and if we solve for that, y squared is equal to 4 minus 4x squared. So what we could do is we can just replace this whole thing by 4 minus 4x squared. So there we go. We have that. We can FOIL it out just to make it a little bit easier for us. So let's see what we're going to have here. We FOIL out the first part. We're going to get x squared and plus 2x plus 1, and then we have a plus 4, and then minus 4 x squared. So what's that simplified to? That's going to simplify to the ones with an x squared terms. We have a -4 and a 1, so that's going to give us a -3 x squared, and then we have 1 plus 4, and that's 5. So everything else is all fixed up, and so that's a nicer polynomial to take the derivative of instead of having to do any fancy rules like chain rule or something like that. Okay, so we have the coefficients for the x squared, the x, and the 5 is a constant, so we'll just submit that. And so we optimize this by taking the derivative of s. So this is your s. S equals to this. S, by the way, now is a function of only one variable, which is good. And so we'll take the derivative of that. And the derivative of this is fairly easy because it's just a second degree polynomial. So this is going to be a -3 times 2. That's -6 x squared. We bring down the 2, and then you subtract 1 from the power. And then we have a 2, and then the 5 is a constant, so that goes away. So we have -6x plus 2. And if we solve for that, we'll bring the 2 on the other side. That'll be negative if we set this equal to 0. Set it equal to 0, and we'll bring the 2 over to the other side. That'll be a -2, and it'll divide by -6. It'll be positive 1/3. So positive 1/3 is going to be our value. So that is the x value that gives us the maximum. So we also they decide that they want to check here to make sure that this is in fact the maximum and not a minimum. So they want us to take the second derivative. If we take the derivative of the first derivative, it's just going to be a -6, and that is always negative. And so when we have a negative second derivative at the critical point, then it's a local maximum. It's a critical point, it has slope 0, and it's concave down, so it's a maximum. And then it turns out that there's going to be 2 y values for this one x value, because when you solve for this thing, and then you're going to get x is equal to 1/3. You want to put it back into your ellipse equation so that you can find out what the x value is. So if we put x is equal to 1/3, we're going to solve for a y value. So let's see how we can do that. So solving for y, we're going to say this is 4/9. So y squared is going to equal to 4, and then we're going to subtract out 4 divided by 3 squared. And so if we find common denominators, this is 36/9, and 36 minus 4 is 32/9. So that's what y squared is equal to, and then when you take the square root, it'll be plus and minus, and this is going to be the square root of 32 divided by 9. So the square root of 32/9. All right. So therefore, the points on the ellipse farthest are as follows. So the smaller value of y is the negative of this thing, and then the larger value of the y is positive of this thing. So what we have here is that 1/3, and then comma, and then we have the negative square root. So let's put a negative, and then let's put the square root, and this is 32/9. And then we'll have the same thing for the other one, except it's a positive. Oops. Oh, bummer. Let's try that again. 1/3 comma, negative square root of 32 over 9, and then I was attempting to copy and paste this and just take out the negative. Okay, so there you have it. Just one more graph to look at. Here is our function. Now if we take a look at the actual distance formula over here with the square root, I actually typed that in over here. If we take a look at how that graph is going to look like. This is the graph, and if we follow this point going down here, if we follow this point, the maximum happens over here. This is 0.33, and then the square root of 32 over 9 must equal to 2.309, and that's a maximum. And then the end point over here has a distance of 2. That's the height of 2, and that's the distance we get when we go all the way over here. So when A, or when our tracer over here is at 1/3, that's going to be our maximum value. All right, hope that helps.